Those giant screens towering over Times Square aren't what you think they are. They're essentially millions of Lego bricks lighting up the sky. Yeah, you heard that right. That massive display blasting advertisements 24/7 isn't one solid piece. It's actually thousands of small tiles, each about the size of a hardcover book, snapped together like the world's most expensive building block set. And here's the kicker. Each one of those tiles is hand-assembled, waterproofed with black goo, and calibrated by a robot camera to make sure every single pixel matches perfectly. Welcome to the insane world of digital billboard manufacturing. Let's talk numbers for a second. The giant billboard in Times Square, it uses over 12 million LEDs. 12 million! That's more LEDs than there are people in New York City. And every single one of those tiny lights had to be soldered onto a circuit board by hand. Well, mostly by machines, but you get the idea. The process is so precise, so ridiculously complex, that one mistake could ruin an entire module. So how do they actually make these things? The module, where it all begins. Everything starts with a small square tile, usually measuring around 320 by 160 millimeters. That's about 12.6 by 6.3 inches for those of us who don't speak metric. This is the module, and it's the basic building block of every digital billboard you've ever seen. Think of it like a single Lego brick, except instead of colorful plastic, it's packed with hundreds of tiny LEDs, resistors, capacitors, and integrated circuits that control the whole light show. The manufacturing process begins with the PCB, the printed circuit board. This green board arrives at the factory completely blank, like a canvas waiting for an artist. Workers slap identification labels on each board for quality control and tracking. Then comes the fun part, applying solder paste. Now, solder paste isn't your regular paste, it's a mixture of tiny solder particles and flux, and it gets applied to specific spots on the circuit board using an automatic stencil machine. Picture a giant mechanical squeegee spreading this metallic goop across the board with surgical precision. The paste acts like temporary glue, holding components in place before the real magic happens. Next up, robots get to work. Surface mount technology machines, SMT machines for short, start placing components onto the board at lightning speed. We're talking resistors, capacitors, integrated circuits, power interfaces, all the electronic guts that make the LEDs work. These machines are so fast and accurate that they can place hundreds of components per minute without making a mistake. Try doing that with your hands. But here's where things get intense. The boards loaded with components enter a reflow oven, basically a high-tech easy-bake oven on steroids. The temperature ramps up gradually to about 150 to 180 degrees Celsius, then cranks up even higher to 235 to 250 degrees Celsius. At this peak temperature, which lasts only 20 to 40 seconds, the solder paste melts and fuses all the components to the board permanently. The temperature control has to be insanely precise. Too hot and you'll fry the components. Too cold and the solder won't bond properly. After soldering, the boards cool down slowly to prevent thermal stress that could crack the connections. Now here's the part that'll blow your mind. They do this twice. After the first round of reflow soldering secures the electronic components, workers apply another layer of solder paste, this time on the lamp surface where the actual LEDs will go. Then comes the LED placement. Hundreds of tiny LED lamp beads get mounted onto the board. Each LED is a miniature light source containing red, green, and blue diodes that can mix together to create millions of colors. The board goes back into the reflow oven for a second time. This second pass solidifies the LEDs in place, creating both a mechanical bond and an electrical connection. Every single LED must be perfectly aligned and securely attached because once these modules are 50 feet in the air on a billboard, you can't exactly reach up and fix a loose bulb. After cooling, each module gets rigorously tested. Power on testing, brightness checks, color calibration. If a module doesn't meet standards, it gets marked for rework or rejected completely. Quality control is everything in this business because one bad module can create a dark spot on a billboard that ruins the entire display. Waterproofing, the black goo that saves everything. So you've got this module packed with sensitive electronics and hundreds of LEDs. Great. Now imagine mounting it on a billboard where it'll face rain, snow, dust, scorching heat, and freezing cold, sometimes all in the same week. Without protection, that module would die faster than your phone battery on 1%. Enter the black goo. Officially, it's called silicone potting compound, but black goo sounds way cooler. This stuff is basically the superhero cape for outdoor electronics. Potting compound is a two-part liquid mixture that looks innocent enough when you pour it. Part A and Part B get mixed together in a precise ratio, usually 1:1 by weight. Once mixed, you've got a limited window to work with it before it starts curing. This is called the pot life, and for typical silicone compounds, it's about 45 minutes at room temperature. Workers, or automated dispensing machines, pour this silicone mixture directly over the LED module's electronics. The liquid is designed to have low viscosity and good flowability, meaning it seeps into every tiny gap and crevice, coating every component. The silicone completely encapsulates the circuit board, creating a protective barrier between the sensitive electronics and the brutal outside world. Why silicone specifically? Because it has some ridiculously good properties. First, it's incredibly flexible, even after it cures into a solid rubber-like material. This flexibility means it can handle vibrations and mechanical stress without cracking. Second, it's waterproof and weatherproof. Rain, humidity, dust, the silicone blocks it all. Third, it can handle extreme temperatures, staying flexible and protective anywhere from -60 to +250 degrees Celsius. And fourth, it conducts heat away from the LEDs, preventing them from overheating and burning out. The potting compound cures either at room temperature over several hours or gets accelerated with heat. Once fully cured, it forms a tough, rubbery coating that essentially mummifies the electronics. Even if water somehow gets on the module, it can't get to the electronics. But wait, there's more. For outdoor modules, the ones destined for billboards exposed to the elements, manufacturers add extra layers of protection. After potting, the modules get a conformal coating, which is like a thin protective paint layer. Then they install a bottom shell or housing made from durable materials with ventilation slots to dissipate heat while keeping water out. Some modules even get a mask installed over the LEDs to protect them physically and reduce glare from sunlight, making the display visible even in bright daylight. This multi-layer waterproofing approach is what allows digital billboards to stay lit 24/7, 365 days a year in any weather condition imaginable. Assembly: building a screen as big as a building. You've got thousands of these waterproof modules ready to go. Now comes the really cool part, putting them all together to create a screen the size of a building. Digital billboards use a modular design for good reason. It's way easier to ship, install, and maintain. Instead of trying to manufacture one gigantic screen in a factory and somehow transport it to Times Square, manufacturers build the billboard in sections that snap together on site. Each module clicks into a cabinet or frame using a latch assembly system. These aren't your wimpy plastic clips. We're talking heavy-duty mechanical latches that lock each module firmly in place while still allowing it to be individually removed from either the front or back of the display if it needs service. The modules slide into mounting channels on the frame, and the latch assembly ensures they're perfectly aligned with their neighbors. Here's where the Lego comparison really hits home. Just like Lego bricks, each module has standardized connection points. The modules connect to each other through power and data cables. Signal cables and power interfaces run between modules, linking them into a unified display system. Thousands of these connections have to be made, and every single one must be secure and weatherproof. For a typical large digital billboard, let's say 14 feet high by 48 feet wide, you might need over 10,000 individual modules. That's 10,000 pieces that have to fit together perfectly with zero gaps between them to create one seamless image. The precision required is insane. If the LEDs are more than a quarter of an LED width out of alignment between modules, installers have to adjust until everything lines up. The assembly happens in stages. Steel beams form the backbone, a massive framework engineered to withstand high winds and support tons of weight. These beams are measured, cut, welded, and bolted together to create a structure strong enough to hold the display. Then comes the real show, Crane Day. Installing a digital billboard requires massive cranes, sometimes 150-ton cranes capable of lifting the display sections high into the air and positioning them with pinpoint accuracy. In windy conditions, lifting these displays becomes especially tricky because the flat LED panels act like giant sails catching the wind. The crane operators and ground crew coordinate carefully, using ropes and spotters to keep everything steady and aligned as they hoist sections into place and bolt them to the steel frame. Some displays get assembled on the ground first, then lifted as complete sections. Others get built piece by piece while already mounted on the structure. Either way, it's a carefully choreographed dance involving specialized crews, expensive equipment, and split-second timing. Calibration, making 12 million pixels match perfectly. All right, your billboard is assembled. Thousands of modules, millions of LEDs, all connected and powered up. You flip the switch and it looks terrible. Some pixels are brighter than others. The colors don't match. One section looks bluish while another looks greenish. Welcome to the calibration nightmare. Here's the problem. Every single LED is slightly different. Manufacturing variability means that even LEDs from the same batch will output different amounts of light when given the same electrical current. Multiply this by 12 million LEDs and you've got a visual disaster. Without calibration, your expensive billboard looks like a patchwork quilt of mismatched colors and brightness levels. The solution? Robot cameras and some seriously smart software. The calibration process starts with a professional-grade camera positioned in front of the display. This isn't your smartphone camera, it's a specialized device that can measure the exact light output and color characteristics of individual pixels. The camera scans the entire screen, collecting pixel-level data on brightness and color for every single LED. This is where the magic happens. The calibration software analyzes all that data and compares each pixel's output to the ideal target values. Then it generates correction factors for each individual LED. If one LED is outputting too much red, the system notes to reduce the current to that red diode. If another LED is too dim, the system increases its current. These correction values get uploaded to the receiving cards, the electronic controllers built into each module that drive the LEDs. The result? A calibration map that tells every single LED exactly how much current it should receive to produce the correct amount of light. When this calibration data is applied, suddenly the patchwork becomes a uniform, smooth image with perfect color accuracy across the entire display. Calibration isn't just about initial setup either. LEDs age over time, and their brightness and color gradually shift. Environmental factors like heat exposure and component aging can introduce new inconsistencies. That's why many high-end digital billboards get recalibrated periodically to maintain optimal image quality throughout their lifetime. Some modern systems even include automatic calibration features that use built-in sensors to monitor and adjust LED performance in real time, keeping the display looking perfect without human intervention. The final product. So there you have it. Those massive digital billboards aren't single screens. They're thousands of carefully crafted modules, each one soldered by machines, waterproofed with silicone goo, snapped together like Lego bricks, and calibrated by robot cameras to create a flawless image visible from blocks away. The next time you see a digital billboard, remember, you're looking at millions of individual LEDs, thousands of individual modules, hundreds of pounds of steel framework, miles of cables, and countless hours of engineering and assembly, all working together to sell you a burger or a new phone. Pretty wild when you think about it. From factory floor to city skyline, digital billboards represent some of the most complex, large-scale electronics manufacturing in the world. And it all starts with one small tile, carefully assembled, one LED at a time. There's something wildly hypnotic about watching an object go from raw material to a finished product in minutes. And when it happens 1 million times a day, that's not just manufacturing, it's a spectacle. In the heart of a modern LED bulb factory, everything moves with a kind of controlled chaos. Conveyor belts whir, robotic arms zip back and forth, and components, tiny, delicate, precise, fall into place like magic. But behind that magic, it's a story of heat sinks, tiny yellow chips, molten plastic, glass domes, and a glowing wall of light where thousands of bulbs are tested in one epic moment. Let's take a walk. No, better yet, let's ride the assembly line. The birth of the body where heat meets shape. Before light can exist, it needs a home. That home, the LED bulb body. It's built to be strong, heat-resistant, and light-friendly. The process begins with placing the aluminum heat sink. That's not just any piece of metal. This is a vital part of the bulb that pulls away heat, keeping things cool even when the light's been on for hours. If it weren't there, the LED chip would burn out faster than you could say eco-friendly. After the heat sink is set, the base of the bulb starts taking shape through injection molding. Picture this. Molten plastic, hot and gooey, being injected into perfectly shaped molds. In seconds, it cools and hardens into the shell that will eventually hold all the inner components. It's fast, precise, and oddly satisfying to watch. Now it's starting to look like something real, not just a blob of plastic and aluminum, but the beginning of something that will one day light up a room. The LED chip, tiny but mighty. At the heart of every LED bulb is a tiny yellow square, the LED chip. Don't let its size fool you. This is the real light maker. It's like the engine in a car or the CPU in a computer. Small but essential. The process kicks off with surface mount technology, or SMT, where these chips are delicately placed onto circuit boards with almost inhuman precision. Machines do this part because the chips are tiny, like really tiny. Trying to place them manually would be like threading a needle while blindfolded, with chopsticks. But for all the machine magic, there's still a human touch involved. Skilled workers step into solder wires onto the direct-on-board DOB LEDPCBS. It's a careful process. Each connection matters. A single weak joint and the bulb might never shine. And then come the IC drivers, little integrated circuits that control how power flows through the bulb. These are separated, sorted, and soldered onto the LEDPCBS, again by hand. Not because machines can't do it, but because these drivers are delicate, and sometimes machines just don't have the finesse. Some LED bulbs are compact, with IC drivers so tightly packed that assembling them by hand is the only option. Add to that certain sockets like the B22, which require hand assembly because automated tools just can't handle the design. It's a blend of automation and craftsmanship that keeps the process flowing. The driver, invisible but essential. Ever wonder how a bulb handles the electricity straight from your wall outlet? That's where the driver comes in. It's the silent workhorse hidden in the base, making sure everything runs smoothly from the moment power hits the socket. Tucked away inside the bulb's foundation is a small but essential circuit board that acts like a translator in taking the high-voltage alternating current, AC, that flows through household wiring and converting it into the low-voltage, steady direct current, DC, that the LED chip requires to shine bright without burning out. Without this component, flipping the switch wouldn't do anything but send raw voltage to a chip that's just not built for it. The journey of the driver begins with delicate precision. First, there's the soldering. Wires must be connected to just the right points, with clean joints that won't fail or under long hours of use. It's not simply about connecting parts, it's about ensuring those connections can handle surges, dips, and constant current flow. The driver board itself is mounted with care, often by hand, especially in more compact bulb designs where machines can't easily reach. These tight configurations demand human finesse, and the workers handling this part are incredibly skilled at making sure every lead is placed perfectly. Some LED bulbs operate with external or modular IC drivers, which are small integrated chips that regulate power flow. Others go the compact route, embedding the driver directly onto the main board. Both approaches have their advantages, but what they share is the absolute need for reliability. These components have to survive thousands of on-off cycles, endure voltage fluctuations, and keep the light steady without flickering or overheating. At this point in the production line, the bulb's internals are beginning to sink. It's a small symphony of micro-components now fully assembled, from chip to board, from wires to drivers. Electricity will enter at one end, travel through carefully soldered paths, get conditioned and converted by the driver, and finally reach the LED chip in just the right form. It's the technical heartbeat of the bulb. Yet, even with all this carefully crafted tech sealed inside, the bulb isn't quite finished. It still needs protection, polish, and proof that everything works the way it should. But for now, it stands as a fully wired promise, ready to turn energy into light with a single flip of a switch. The globe covering the light. With the engine ready and the wiring in place, the next step is to protect and shape the light. That's where the PC cover comes in, the dome-like cover that gives the bulb its familiar look and helps spread the light evenly. It's more than just a finishing touch, it's the diffuser, the final frontier between raw brightness and comfortable illumination. Depending on the design, this dome might be made from either plastic or glass, and each material brings its own character to the bulb. Plastic covers dominate most production lines due to their lightweight and durability, and the way they're made is nothing short of mesmerizing. The process begins with injection molding, molten plastic heated to the perfect temperature, then shot into molds that give it that smooth, curved shape. Once cooled, the covers are crystal clear or gently frosted, depending on the desired lighting effect. In some specialized production lines, the classic charm of glass is still used. It's a slower, more delicate process involving glass blowing, shaping the red-hot material into seamless domes before letting them cool into a pristine, transparent shell. Whether glass or plastic, each dome must be flawless. Any bubbles, warps, or scratches can affect how the light disperses. When ready, these domes are moved to the assembly line, where robotic arms take over. With sharp, precise movements, the arms grip each cover, rotate it gently, and lower it onto the bulb body. The alignment is spot on, no guesswork here, and the snap into place happens in one smooth, satisfying motion. But snapping alone isn't enough when the bulb will face years of heat and pressure. That's where adhesive comes in. A tiny bead of high-performance glue is applied at the base of the cover. It's clear, strong, and built to last. It ensures the dome doesn't shift, crack, or loosen over time. Once sealed, the bulb gets one step closer to completion. This entire process happens in seconds, repeated over and over across thousands of units per hour. And the result? A perfectly shaped light diffuser that not only protects the internals, but also softens and spreads the glow into something comfortable, familiar, and pleasant. The dome isn't just functional, it's what makes the bulb instantly recognizable on store shelves, and in every room it eventually lights up. Watching this part of the process unfold feels a bit like watching high-tech ballet, a dance between heat, precision, and polish. Semi-automatic magic. Humans plus machines. Here's where things get really cool. The semi-automatic production line. It's part machine, part human, and all efficiency. Workers place the assembled PCB into the bulb base and feed it into the machine. It presses everything into place with just the right amount of force. The machine also leaves enough room for the PC cover to be added later. Spacing is everything here. Next comes the socket. Whether it's an E27 or B22 base, the socket is added and locked in. Some are screwed, some are clipped, but every one of them has to be snug. A loose socket is a safety hazard, and this process doesn't allow for mistakes. Even at this speed, rotating with thousands of bulbs moving per hour, every single one is handled with care. The aging rack, a wall of light. Now comes the moment of truth, and the factory seems to hold its breath as testing begins in full force, because this is where every shortcut, every tiny imperfection, and every hidden flaw finally reveals itself under bright, unforgiving light. Each finished bulb is guided onto the aging rack, a towering structure that stretches like a glowing wall across the factory floor, sometimes carrying 10,000 bulbs at the same time. When the power flows in, the rack comes alive instantly, flooding the space with an intense, uniform brightness. The sudden glow feels almost theatrical, like curtains lifting on a stage made entirely of light. This step isn't rushed because time is part of the test. The bulbs stay on for hours, sometimes longer, to simulate real-world use long before they ever reach a home or office. Heat slowly builds, and that heat tells a story. Weak components show their limits here. A poorly soldered joint might flicker. A stressed driver might dim unexpectedly. A flawed LED chip might fail altogether. The goal is simple but strict. Only the strongest survive. Technicians move calmly along the rows, eyes trained to catch even the slightest change in brightness. A bulb that hesitates, pulses, or goes dark is immediately removed without hesitation. There's no second chance at this stage. Every glowing point of light represents consistency, reliability, and safety. The hum of electricity blends with the quiet footsteps of inspectors, creating a steady rhythm across the floor. The air feels warmer near the racks, a reminder of how much energy is flowing through those tiny components. From a distance, the racks resemble a city skyline at night, dense and glowing, perfectly ordered. Up close, each bulb feels individual, each one proving it can handle the job. This process also stabilizes the bulbs, weeding out early failures before customers ever see them. It's a silent promise of longevity. Watching thousands of bulbs burn steadily at once is strangely calming despite the industrial setting. The light is clean even and reassuring. In that moment, the factory doesn't feel like a factory at all. It feels like a place where reliability is forged, one glowing bulb at a time. Final touches, polishing and packing. After testing, the bulbs move to the final stage. Covers are cleaned, smudges removed, and each unit is checked one last time. Then they're packed, rows of clean, tested bulbs ready to be boxed up and shipped around the world. It's hard to believe that just minutes earlier, these bulbs were a pile of plastic, aluminum, and silicon. Now they're ready to light homes, offices, shops, and streets. The whole process, from raw material to glowing bulb, is a stunning dance of heat, precision, and light. And when it's scaled up to 1 million units a day, that's not just manufacturing, that's brilliance in motion. LED bulbs might seem simple, just a light source, right? But behind every glow is a story of engineering, design, speed, and human ingenuity. From heat sinks to chips, from plastic domes to glowing walls of light, each one is a little miracle of modern production. And the fact that 1 million of them are made every single day? That's the kind of stat that deserves respect. Every day, people unlock their phones without thinking twice, but inside that sleek device is one of the most complex machines ever built. It all begins in a place buzzing with energy. Noida, India. Not just any city. This is where Samsung runs the biggest phone factory on the planet. Imagine walking into a space that spans over 129,000 square meters. That's more than 18 football fields laid side by side. The air hums with the synchronized rhythm of machines and humans working in harmony. This factory doesn't just make phones for India, it makes them for the world. Over 120 million of them every single year. Noida isn't just building devices, it's a symbol. It's where Make in India meets Make for the World. When the facility was inaugurated in 2018, India's Prime Minister himself flagged off the vision. Since then, this place has become the global brain of Samsung's mobile manufacturing, contributing nearly 25% of Samsung's global phone output. It all starts with a brain, and by brain, think of the motherboard. This isn't just a slab of silicon, it's a multi-layered marvel. It begins with a bare PCB, a blank canvas, but within seconds, robots buzz to life, placing thousands of components, resistors, capacitors, chips with astonishing speed and pinpoint accuracy. Each SMT machine is a beast in itself, capable of placing over 3,000 tiny components in the time it takes to blink. The process feels like watching a futuristic ballet. Paste is applied with surgical precision, components are mounted, and then the board goes through a nitrogen oven. This massive furnace slowly bakes the layers, ensuring every component is fused just right. Then the board flips. The same steps repeat on the other side. Every tiny part has a job and nothing goes to waste. The alignment needs to be so perfect that even a 1-degree deviation can break the entire circuit. These machines operate under strict temperature control because even a small thermal shift could warp a connection. The paste used to attach components is carefully formulated to withstand heat and vibration. When the board exits the oven, it's inspected again, not by eyes, but by AI-powered cameras that never miss a detail. Optical systems scan for micro cracks invisible to the human eye. It's here that a decision is made, pass or fail, within milliseconds. Boards that don't pass are automatically routed to a diagnostic station where specialists determine the flaw. Meanwhile, flawless boards move forward, advancing like VIPs to the next stage. It's easy to forget that each of these boards is the beginning of a smartphone that might soon power someone's life. That board might end up in a school child's first phone, or a traveler's GPS, or a business owner's lifeline. Each one starts here, under the robotic arms and infrared lights designed to be tough but built with elegance. Even the sequence of the components, where each resistor, each capacitor is placed, is optimized to reduce power loss and increase efficiency. This isn't just about making phones fast, it's about making them better every time. What's wild is that every SMT line operates differently based on the phone model it's producing. One line might be working on a flagship, while another is assembling an entry-level device. The software driving each SMT machine is constantly updated, often remotely, by engineers monitoring performance trends in real time. This digital nervous system connects every corner of the factory, from ovens to optical scanners, from conveyors to cloud dashboards. It's smart manufacturing on a scale that's hard to imagine. Maintenance teams walk the floor, checking calibration, ensuring no nozzle is misaligned, no feed tray runs empty. At any moment, alerts can notify the floor team if a placement is even slightly off-center. Every machine has backup systems, every line has fail-safes. It's a fortress of accuracy. What happens in this SMT stage affects the entire life of the phone. A perfect board means fewer issues down the line, better battery life, better performance, and better user satisfaction. And because these machines are pushing limits daily, there's always a team of software and hardware engineers on standby, fine-tuning algorithms that guide these microscopic placements. The precision isn't just mechanical, it's emotional. There's pride built into every layer, pride that this factory in India is setting the bar for global production. Here, technology isn't just built, it's elevated, but it doesn't stop there. Inspection stations dot the production line using optical recognition and AI to catch the tiniest defects. These aren't just checks, they're safeguards. And after passing inspection, the motherboard transforms into a fully operational PCBA. It's ready for action. With the brain built, it's time to give the phone its face. The screen, sleek, fragile, and essential. To fuse the OLED and glass without a speck of dust getting in, the process takes place in vacuum chambers. Here, the environment is as sterile as a surgical room. Every bubble is eliminated. Every alignment is perfect. The slightest speck of dust can ruin the entire display. That's how delicate and demanding this phase is. And once the screen is ready, the next stage is where automation hits overdrive. Robotic arms place the screen onto the frame, sealing it in a way that no human could. The display isn't just slapped on. It's pressed at precise angles, especially for curved edges seen in flagship models. These tiny components are what allow screens to dim, calls to mute, and faces to unlock phones instantly. Each sensor is checked as soon as it's connected. Batteries slide into position next, sealed carefully, because safety is everything at this stage. No shortcuts, no assumptions. Throughout this process, phones keep moving, never stopping for long. Overhead screens track progress in real time, showing which unit is where and how long it's been there. If a delay happens, systems respond immediately. Another line compensates, another robot steps in. The rhythm never breaks. What stands out most here is balance. Humans and machines share the space without conflict. Robots handle repetition and precision. Humans bring judgment and adaptability. Together, they make sure every phone leaving this line feels exactly the way it should in someone's hand. By the end of this stage, the phone isn't just assembled, it's alive. The screen lights up, the system boots. A device that started as raw materials is now something ready to connect, capture, and communicate. And yet, even now, it's not done. The toughest challenges are still ahead, and the tests begin. There's the airtightness check. Not once, but multiple times. Instead of water, air pressure is used to simulate waterproofing. Fail the test, the unit gets pulled out, disassembled, and diagnosed. Only the flawless continue. But the real thrill, the drop test chamber. Some call it the torture room. Robots drop phones from all angles, on concrete, on metal, on glass, up to 100 times. It's brutal, it's necessary. The goal: ensure that the screen doesn't shatter and the internals don't get knocked loose. And then function testing takes over. Robots simulate real-world use. Scrolling, tapping, typing, shooting videos, making calls. AI tracks power consumption, app performance, antenna signal strength, and more. There's even a special robot that doom scrolls TikTok all day long, testing battery drain under realistic scenarios. Nearby, rows of phones are tested in a fully automated microwave lab. These chambers test signal reception and transmission under conditions that mimic real-world usage, including body interference. Robots adjust phones to millimeter precision, ensuring every test is exact. Behind the scenes, data pours into terminals that engineers use to tweak future models. In another lab, engineers are testing materials, how glass reacts to UV rays, how hinges survive millions of folds, how polymers wear over time. Machines simulate years of use in hours. These stress tests are what make foldables durable and phones last longer. This level of precision ensures the phone works flawlessly under any condition. It's fascinating to see how every component has a role, no matter how small. Every stage of production is tuned like an orchestra, where machines and humans work in perfect harmony. Samsung's commitment to quality isn't just a slogan, it's built into every layer of the phone. From microscopic resistors to the glowing OLED screen, each part is a testament to engineering brilliance. The factory is alive not with chaos, but with rhythm, a carefully timed dance of technology. Robots aren't just assembling, they're thinking, learning, improving every cycle. In a single day, thousands of phones pass through these lines, each one a marvel of manufacturing. Behind every smartphone is a story of effort, innovation, and relentless testing. This isn't just production, it's perfection at scale. Every product is tracked, logged, and scanned dozens of times before it ever reaches a store shelf. This level of consistency is why phones from this facility are trusted by millions around the globe. All of this is supported by India's own research muscle. Samsung operates multiple R&D centers here, staffed by young engineers developing AI features that power the latest Galaxy devices. These teams contribute to everything from voice recognition to camera algorithms. It's not just manufacturing, it's innovation born and tested in India. And while Samsung's Galaxy AI-powered phones are assembled here, the factory doesn't stop at mobiles. Tablets and even premium AI appliances like refrigerators are also built under the same roof. It's a connected ecosystem built with precision and shipped across continents. This is the stage where all the hard work finally becomes visible. What once looked like scattered parts now starts to resemble something familiar. Frames glide in on conveyors, perfectly timed, never rushing, never waiting. The motherboard settles into place like it was always meant to be there. Cooling paste is applied in precise amounts, just enough to keep performance stable without wasting a drop. Every screw is tightened with calibrated force because too loose or too tight can change everything. Cameras are installed next, and this isn't just about plugging something in. Alignment here is critical. Even a fraction of a millimeter can affect focus, clarity, and image stabilization. Machines guide the placement, but humans supervise closely, watching for anything that feels off. Speakers are tested the moment they're seated, sending quick pulses of sound to confirm clarity and balance. If something doesn't sound right, the phone doesn't move forward, sensors are layered in quietly, almost invisibly. These tiny components are what allow screens to dim, calls to mute, and faces to unlock phones instantly. Each sensor is checked as soon as it's connected. Batteries slide into position next, sealed carefully, because safety is everything at this stage. No shortcuts, no assumptions. Throughout this process, phones keep moving, never stopping for long. Overhead screens track progress in real time, showing which unit is where and how long it's been there. If a delay happens, systems respond immediately, another line compensates, another robot steps in, the rhythm never breaks. What stands out most here is balance. Humans and machines share the space without conflict. Robots handle repetition and precision. Humans bring judgment and adaptability. Together, they make sure every phone leaving this line feels exactly the way it should in someone's hand. By the end of this stage, the phone isn't just assembled, it's alive. The screen lights up, the system boots. A device that started as raw materials is now something ready to connect, capture, and communicate. And yet, even now, it's not done. The toughest challenges are still ahead. The entire process is a showcase of synergy. Humans and machines, design and durability, software and hardware, all coming together to build devices that billions use every day. And after the testing and inspections are done, the final step begins. Packaging. The factory hums as mini robots carry finished boxes, routing them to shipping lines. What started as a tiny PCB has now become a fully functional smartphone, ready to go global. The Noida factory isn't just big, it's smart, strategic, and a sign of how far India has come in tech manufacturing. With 120 million phones produced annually, this is more than a plant. It's a powerhouse, a symbol of vision, execution, and innovation. Every year, more than 200 million televisions are sold worldwide, finding their way into homes, offices, restaurants, and nearly every corner of daily life. The television has become more than just a screen to watch shows and movies. It is a window to the world, a hub for information, and a centerpiece of modern entertainment. But behind the sleek design, the vivid images, and the endless hours of content lies an extraordinary story of engineering, precision, and collaboration. Few people ever get the chance to see how these remarkable machines are brought to life. So today, the journey begins inside one of the largest television factories in the world, a place where machines and workers move in perfect synchronization to transform sheets of glass, tiny electronic components, and liquid crystals into the giant screens that dominate living rooms everywhere. This mega facility is truly a technological wonder in itself. Stretching across over 1 million square meters, it is a space the size of a small city. Within its vast walls, nearly 500,000 smart televisions are produced each year. The focus here is on large screens, the type of televisions that have become the centerpiece of modern households. Every corner of the factory is carefully designed for efficiency, where the hum of machinery blends with the swift, precise motions of skilled workers, creating a choreography that produces televisions on a massive scale. The sheer scale of the production floor can feel overwhelming at first, with conveyor belts running endlessly in different directions and machines rhythmically operating in perfect sequence. Specialized zones are set up for each stage of production, ensuring that every step flows smoothly into the next without delay. Automated vehicles glide silently across polished floors, transporting panels and components with clockwork accuracy. Workers dressed in matching uniforms move in unison like parts of a larger machine, each one focused on a task that contributes to the greater whole. Bright overhead lighting illuminates every corner, giving the impression of a space that never truly rests. Even during quieter moments, the atmosphere is charged with purpose, as though the factory itself breathes with life. Gigantic storage racks line the walls, stacked high with raw materials ready to be transformed into finished products. Robotic arms pivot with mechanical grace, lifting, rotating, and placing fragile parts without the slightest hesitation. The combination of human intuition and automated precision creates a balance that neither could achieve alone. Every workstation has been optimized for speed and accuracy, reducing wasted time and minimizing errors. Monitors display live production data, showing the output in real time and keeping the pace steady and consistent. Engineers keep a close eye on these figures, ready to make adjustments at a moment's notice to prevent bottlenecks. Safety is also a key priority here, with every worker trained to handle sensitive components carefully while following strict guidelines. The factory hums like a giant engine, where each sound, from the whir of cooling fans to the faint clicks of tools, is part of a larger symphony. Walking through the aisles, one can sense that the facility is designed not just for productivity, but for longevity, capable of meeting growing global demand for years to come. The heart of every modern television is its screen, and that is where the process begins. Unlike older, bulky models, today's televisions rely on liquid crystal display panels. These flat screens are not only thinner and lighter, but also capable of producing much brighter and more vibrant images. Compared to older cathode ray tube televisions, the difference is astounding. Modern flat screens bring clarity and color into homes that past generations could never have imagined. Yet, achieving such visual brilliance requires a manufacturing process that is both delicate and incredibly complex. The journey of creating a screen starts with materials that appear simple but demand extraordinary precision. Sheets of glass, polished until flawless, are carefully inspected to ensure they are free from even the smallest imperfection. These sheets form the foundation upon which billions of images will one day appear. The transition from thick, heavy tubes to razor-thin panels has completely changed not only how televisions look, but also how they fit into daily life. A screen that can hang like a picture frame on a wall is the result of decades of refinement in engineering. Unlike the fuzzy, curved glow of old cathode ray sets, these displays offer razor-sharp lines, vivid color contrasts, and a level of detail that feels almost lifelike. But the technology that allows such beauty to emerge is hidden beneath layers so fine they can barely be seen with the naked eye. Inside every screen is an orchestra of microscopic components working together, each one controlled with absolute accuracy. It is fascinating to realize that what looks like a simple surface is actually an intricate network, where millions of pixels are waiting to be lit in perfect harmony. The demand for bigger, brighter, and thinner televisions continues to push the limits of what manufacturers can achieve. Every advancement in screen technology represents years of experimentation and refinement, building upon earlier successes while overcoming countless challenges. The screen is more than just a display. It is the identity of the television, the very feature that defines the experience for viewers. Without the brilliance of modern display panels, the stories, colors, and emotions brought into homes through television would lose much of their magic. Creating a panel is not only about science, it is also about capturing the imagination, transforming raw glass into a portal that connects people to worlds far beyond their own. The first step takes place in a highly controlled clean room. The reason for this environment is simple. Any speck of dust or impurity could ruin an entire screen. Workers in specialized suits, resembling something out of a science fiction film, carefully handle sheets of glass that are destined to become the foundation of a television display. Glass is the largest single component of a flat screen and serves as the canvas upon which millions of tiny electronic miracles will soon be created. These screens are built by sandwiching together two thin sheets of glass. On one of them, a layer of silicon is deposited, and then begins a painstaking process of constructing millions of microscopic transistors. Each transistor will one day control a pixel on the screen, the tiny dot of light that forms part of the television's image. The scale of this construction is mind-boggling. To the naked eye, the glass may appear unchanged, but under magnification, one can see the vast network of transistors carefully etched across its surface. The process is repeated over and over until millions of individual cells are formed. Meanwhile, the second sheet of glass undergoes a transformation of its own. Here, a matrix of red, green, and blue subpixels, known as a color filter array, is created. Each pixel of the television is made up of these three subpixels, and by combining them in varying intensities, the screen can produce over 1 billion colors. The precision required is immense, because even a single faulty pixel could ruin the viewing experience. Once both sheets are ready, tiny amounts of liquid crystal material are inserted between them, and then the two sheets are bonded together. This delicate liquid crystal layer is what gives the display its name, allowing light to be controlled with extraordinary precision. However, liquid crystals cannot shine on their own. They need a source of light, and this is where LEDs come into play. The factory uses specialized machines to place rows of light-emitting diodes onto strips. The challenge is that the light from these tiny LEDs must be spread evenly across screens that can stretch more than 1.5 meters wide. The solution comes in the form of transparent plastic sheets known as plexiglass. Light entering one side of the sheet is scattered throughout its entire surface, creating a uniform glow. To enhance brightness and color, 2 additional optical films are carefully added, each engineered to boost the display's performance. At this point, the panel is ready to be framed. Injection molding machines produce strong plastic casings in various sizes, molded under high pressure to ensure durability and precision. These casings form the front and back frames of the television, giving structure to the otherwise delicate screen. Workers and robotic arms place the panel inside the frame, and slowly the television begins to take on its familiar shape. But a screen alone cannot make a television function. To bring it to life, a brain must be installed. This brain comes in the form of the main board, known as the SSB, and the power supply board, called the PSB. Both are manufactured right here in the factory. The SSB processes all of the television's data, running complex algorithms to ensure smooth images and clear sound. The PSB, meanwhile, regulates the electricity flowing through the device, ensuring that everything operates safely and efficiently. Other specialized boards are also installed, including control boards on the sides of the panel, a board for the remote control receiver, and even one for Wi-Fi connectivity. Creating these boards is a process of its own. Thousands of tiny components must be placed onto motherboards with precision. Machines work tirelessly, positioning each piece one by one, faster than the human eye can follow. Once assembled, the boards are run through a wave soldering machine, which electrically connects all the components in a single pass, ensuring a strong and reliable connection. Skilled workers then inspect and complete each board, preparing it to be mounted into the television body. As the assembly line moves forward, workers carefully screw the boards into the back covers of the televisions. Even here, precision is everything. The electric screwdrivers are carefully calibrated to apply just the right amount of torque, preventing any damage to the delicate components. Suspended from above, the tools are designed to reduce worker fatigue, ensuring consistency throughout long shifts. With the electronic brains in place, the televisions are almost ready to awaken. The next stop is the testing area, where each unit undergoes rigorous checks. Here, specialized machines load the necessary software and data into the television's memory. This allows the device to boot up for the very first time. Watching rows of brand new screens light up for their inaugural test is a remarkable sight. At this stage, each television is turned on vertically, allowing workers to perform visual and electronic inspections. Colors are tested, pixels are examined, and every component is checked for proper function. Highly sensitive scanners focus on key areas, detecting defects that the human eye might miss. A single inactive pixel is enough to disqualify a unit, as the factory's standards are uncompromising. The average lifespan of these modern displays is estimated at 100,000 hours. To put that in perspective, it means a television could run continuously for over 11 years before reaching the end of its life expectancy. Achieving such durability requires not just advanced materials, but also relentless quality control. High-definition screens contain more than 2 million pixels, each with 3 subpixels. Together, they are capable of displaying over 1 billion shades of color, creating the rich and lifelike images viewers expect. Before leaving the factory floor, each television endures a rigorous final quality control process. For a minimum of 4 hours, the screens are tested under different conditions, ensuring stability, brightness, and accuracy. Skilled experts oversee this stage, monitoring every detail to confirm that each television meets strict standards. Only after passing this final examination can a television be considered ready for the world beyond the factory walls. Once approved, the televisions are hand-packed into sturdy cardboard boxes. Each package is carefully designed to protect the device during transport with special inserts that prevent movement or shock. At the end of the assembly line, hundreds of boxed televisions are stacked onto pallets, forming towering columns of screens awaiting shipment. Trucks back into loading bays, and forklifts carry the pallets on board. From there, the televisions begin their journey, traveling across cities, countries, and continents until they reach the living rooms of eager customers. What began as fragile sheets of glass and tiny electronic parts has now become one of the most important devices of modern life. The journey from raw materials to finished product is one of precision, innovation, and teamwork on an enormous scale. Every step, from the delicate handling of liquid crystals to the powerful machines that mold casings and solder circuits, contributes to creating the vivid images that entertain, inform, and connect the world. Televisions may appear simple on the outside, just a screen mounted on a stand or hung on a wall, but inside lies a symphony of technology, perfected over decades of innovation. Factories like this one are the hidden engines behind the entertainment that millions enjoy every day. Each television carries within it not only the power of technology, but also the dedication of countless individuals who make sure every detail is flawless before it ever reaches a home. And with that, the story of how televisions are made reaches its conclusion. From sheets of glass to vibrant screens, from tiny circuits to breathtaking images, the process is a remarkable blend of science, engineering, and human skill. If this journey inside the world's biggest television factory was fascinating, don't forget to give this video a thumbs up. Share it with someone who would enjoy learning about it, and subscribe to the channel. Turn on notifications so you never miss out on more stories about how the world's most incredible machines are made. Thanks for watching.